Alright, so let us discuss the applications of the Ampere's circuital law. Ampere's circuital law has a number of applications. The first one is magnetic field due to an infinitely long straight current carrying wire. Okay, so every word in this heading is important. Magnetic field due to what? An infinitely long straight current carrying wire. Let me draw the diagram first of all. So let's say we have a wire. So we have a wire which is quite long. Okay, a long wire in this manner. So let's say this point is X and this point is Y. There's a current flowing in the wire in that direction. So let's say a current I is flowing. Okay. Now what do? We take a loop. Now in order to apply the Ampere's circuital law, we have to consider a closed loop. You remember or not, we use the same concept in the Gauss law. Remember, to find the electric field, what did we do? We consider a small we consider the Gaussian surface, a closed Gaussian surface. Yes or no? So similarly here, we will not consider a surface, instead we will consider a closed loop. Okay, and this loop, let us take it to be in circular in shape. Okay, let's say you have this closed loop like that. Okay, so that is a closed loop, and where is this closed loop? It is on this surface, just like before. On this surface, let's say. Alright, so that this wire is coming from here. It enters through the surface and it comes back from below the surface. Got it? Just like before, the same concept. So to apply the circuital law, we have to take a small length. We have to take what? A small length of the loop. Okay, so let's take a small length dl. Okay, from here till here. So let's say that is a small length dl. Okay, dl, right? Okay, and at this point, what will be the direction of the magnetic field? The magnetic field will be in this direction, tangential. It'll be tangential, like that. Got it? And the distance from the wire to dl, this distance is denoted by r. Okay, which is the radius of this loop. Okay, so by Ampere's law, we have B dot dl, this is equal to mu naught I. Yes, again you apply the A dot B formula. A dot B formula, we know that it is AB cos theta, so this will be B dl cos theta. What is theta? Theta is the angle between B and dl, and it's very clear in the diagram that dl and B are pointing in the same direction, so the angle between them is 0 degree. So this will be mu naught I. So that will be B dl. Why? Since cos of 0 degree, that is equal to 1. So that will be mu naught I. Okay, this b I can take it out. Integration of dl is equal to mu naught I. And again, just like before, I'm taking dl. When I integrate, I get the circumference of the circle, and that is equal to 2 pi r. Therefore, take this 2 pi r to the right hand side, you get b is equal to mu naught I by 2 pi r. That is the required expression. Okay, now if suppose the yeah, that's it. Yeah, suppose okay, if you look at this expression out here, what is the, I mean, how does the magnetic field vary with the distance? It is inversely proportional to the distance r. So this distance is still here, but suppose if I take farther distance, okay, farther, if I go farther and farther away from the wire, what will happen to the magnetic field? The magnetic field will decrease, right? So why? Because if r increase, then this magnetic field will decrease. Got it? If r is very large, it becomes infinite, then in that case the magnetic field will be 0. Okay, so that's one application. That's the first application of the Ampere's second law. I will discuss more applications in the next videos.